Current text to 3D diffusion models struggle with consistent physical reality. They frequently output meshes with melted details, artificially thick surfaces, and entirely collapsed internal cavities. The source of this bottleneck is the industry's near-universal reliance on distance fields, specifically signed or unsigned distance fields, and the marching cubes algorithm used to extract their isosurfaces. These traditional pipelines require strict watertight preprocessing. To compute a continuous field, the algorithm has to determine a global positive or negative sign to define the inside and outside of an object. This violently forces open or non-manifold geometries into closed boundaries. The visual consequences are immediate. The algorithms overcompensate on thin geometry, creating artificial surface thickening. They introduce jagged, stair-step artifacts along the extracted isosurfaces. And because of the global inside-out calculation, complex topologies like rooms within rooms are completely erased. Models can scale to massive parameter counts, but as long as the reconstruction relies on implicit distance fields and marching cubes, 3D generative AI will remain trapped under a hard mathematical ceiling of geometric fidelity. Bypassing this ceiling requires an explicit methodology. Rather than converting a mesh into a field function, we need a system that operates directly on the raw, non-manifold data. Think of the traditional distance field approach like navigating a dark room using a sonar sensor. The signal only registers the distance to the nearest wall, forcing the system to map the geometry by guessing exactly where that distance equals 0. Open surfaces and internal structures completely break this assumption. The sonar fails to differentiate the interior of a room from the hallway outside, causing the global sign calculation to collapse. The faithful contouring approach acts like a digital blueprint. Instead of guessing distances through a continuous field, the algorithm explicitly plots exactly where the architectural lines intersect a high-resolution 3D grid. By directly identifying the voxels that intersect the surface, we abandon isosurface extraction entirely, resulting in a near-lossless, voxelized 3D representation. The process begins with the faithful contour token encoder. The system performs a multi-level octree traversal on the raw mesh, scaling from a coarse minimum resolution all the way up to a highly detailed 2048 cubed grid. To handle this massive scale, the encoder runs fast, CUDA-accelerated axis-aligned bounding box tests. These intersection checks instantly prune empty space, isolating only the active cells that actually contain surface geometry. Inside a single active voxel, the system relies on a structure similar to a tent pole and surrounding pegs, a center support combined with tension points to hold the geometry taut. The pole is the primal anchor. It is a single plotted point containing absolute position and normal data, representing the primary intersection of the surface within that specific voxel. The pegs are the dual anchors. These provide up to 8 additional positions and normals, equipped with a mask to map the topological context directly surrounding the primal point. Finally, the system registers the semi-axis orientations, 6 directional flags along the X, Y, and Z axes that dictate the precise connectivity between the primal anchor and its neighboring voxels. The encoder outputs this data into 2 highly compact tensors, an index of the active voxels, and a features tensor mapping K voxels to exactly 69 data channels each.
This 69-channel token resolves all continuous geometric ambiguity. It translates complex, raw 3D mesh data into a strict, predictable numerical format, perfectly optimized for neural networks. Decoding this format reverses the process. The FCT decoder ingests the tokenized tensors and calculates the absolute world space positions of all the stored primal and dual anchors. Using quad reconstruction, vector reorientation, and final triangulation, the decoder connects the primal points to their valid dual neighbors. This fully restores the original mesh topology without ever calculating a global field. To prove these tokens are viable for generative AI, researchers implemented a custom sparse variational autoencoder, or VAE, designed specifically to compress faithful contour tokens. The critical feature of this VAE is its dual-mode input capacity. In auto-compression mode, the network encodes structure FCT tensors into compact latent codes, then decodes them back with near-lossless fidelity. In point-to-FCT mode, local attention layers ingest unstructured, chaotic point clouds. The network aggregates these sparse point features into explicit voxels and outputs the highly structured FCT format. This dual mode bridges the gap between raw data and structured representation. Generative models can train on massive, unstructured datasets, natively outputting machine learning-ready contour representations to transform the entire industry. The empirical results establish a new baseline for representation. Faithful contouring achieves a 93% reduction in chamfer distance and a 35% improvement in F-score compared to strong existing baselines like Spark. This image shows a close-up of an armored warrior processed through the FCT pipeline.
The geometric distance errors here sit exactly at the 10 to the negative fifth level, capturing the pristine, unmelted details of the intricate chest plating. This image shows a close-up of mechanical joints on a bipedal robot. By relying on local anchor fitting, the algorithm produces clean, single-layer geometries, eliminating the double-layer artifacts and voxel bumping that plague flood fill and UDF methods. This image shows a semi-transparent wireframe motorcycle. The internal engine block and suspension coils remain perfectly intact, precisely the internal geometries that marching cubes routinely destroys. These outputs are the direct mathematical result of abandoning isosurface extraction in favor of explicit, voxelized tokenization. The processing methodology here is entirely local and highly parallelizable. Because it skips rendering optimization, the CUDA execution scales effectively to massive resolutions without proportionate computational drag. The implementation does currently rely heavily on specific CUDA environments and C++ compilers. Additionally, researchers note that extreme, non-standard geometric topologies will require further testing to guarantee absolute robustness. The immediate next step for this framework is differentiable contouring. Integrating these tokens natively into gradient-based learning pipelines will allow massive diffusion models to directly generate explicit, high-fidelity 3D geometry. Here are the 3 key takeaways for researchers. 1. Distance fields and marching cubes are active bottlenecks preventing high-fidelity 3D generation. 2. Fateful contouring solves this by using local voxel anchors, scaling efficiently past 2048 cubed resolutions. 3. Paired with dual-mode VAE compression, faithful contour tokens provide the precise structural format required for the next generation of 3D generative AI.